Okay, we have been doing a lot on differentiation. We're now going to start going in the opposite direction. We're going to start undoing differentiation and do the antiderivative, also known as integration. Very simple, straightforward, most of it. For example, you're very familiar with the idea, if I had the function y is equal to 6x squared plus 3x plus 1, that's going to derive to give me 12x plus 3. And it really wouldn't matter what I had on the end here. I could have plus 10, I'd still have the same derivative. I could have plus 100, I'd still have the same derivative. So integration is I would undo the 12x plus 3 to arrive back at what I started at. So if the symbol for integration is that funny looking thing. So if I did the integral of 12x plus 3, I've got to put this on the end, dx, just like we did dy dx, so the derivative of y with respect to x. Here we also do the integral of this function with respect to x, so you need the symbol at the front and the dx indicating what the variable is at the back. And so the undoing of it is 12 is a constant. Constants are constants because they are constantly there. It doesn't partake in the differentiation or the integration. 12 stays there. X to the power 1 goes up to become x to the power 2, and then I divide through by 2. 3, it's currently 3 lots of x to the power 0, so it becomes 3 lots of x to the power 1 divided by 1. And as I said, it doesn't matter what number I have on the end here, it derives to the same thing, so I could have any particular value on the end. So the integral is going to be 6x squared plus 3x plus some particular constant. So that's just straightforward integration for a normal function. We're going to have a look at a couple of situations where we're doing integration on things that are a little bit more complicated. For example, we know that if I had y was equal to the natural log of x, it derives to be 1 on x. So a first rule that I want to look at is I'm going to do the integral of 1 on x dx must be the natural log of x. Now, I can multiply this through by any particular constant I want. So if I had it times by some constant there, the derivative has to be times by some particular constant there as well. Let's not forget our plus c on the end. So there's our first rule. Remember, 1 on x integrates back to be the natural log of x. Constants just stay there. Okay, example number 2. Now, if you've got this situation here where you want to do the integral of, let's say you have some particular function on the bottom of a fraction, and you have the derivative of that function on the top, dx. If you want to integrate that follows the pattern like this. It just integrates to be the natural log of whatever that function on the bottom is, plus c. So our example for that would be, so if I wanted to do the integral of 6x over 3x squared plus 4. So to integrate that, I check, do I have the situation where I have a function on the bottom and its differential on the top? 3x squared plus 4, differential of that is 6x. Yes, I have the differential on the top, function on the bottom. That's just going to integrate straight to the natural log of 3x squared plus 4, all plus c. And you know how to do chain rule and do differentiation of natural logs. You can check that if you like. Do the differential of that, and you'll arrive back at this situation here. Now, I'm going to throw in a bit of a variation. Let me just give a moment to clear the board, and I'm going to do exactly the same question with just a little bit of a twist to throw it in. Now, what would happen in this situation where I haven't quite got this scenario here? I've got a function on the bottom, 5x plus 2. Its derivative is 5. I don't have 5 on the top. Can I still apply this? Well, yes I can. I can modify this to make it look like what I want it to do. I need 5 on the top. So if I went through, now outside this integral sign I'm allowed to multiply through with constants. If I multiplied the top line by 5, of course I'm going to have to multiply the bottom line by 5 as well to keep it nice and equal. I now have the situation that I'm actually looking for. I now have, if you like, multiply this 5 across the top. I have 5 there over 5x plus 2, and I want to integrate that with respect to x. I've used the 5 on the top, I haven't used the 5 on the bottom yet, so I'll just leave it out the front as is. This situation here behind the integral sign now matches this scenario here. So it's just going to integrate to be the natural log 5x plus 2 plus 7. Constants are constants because they are constantly there, they don't partake in the integration, so I have my 1/5 out the front as well. I could put it all over 5 if I wanted, it means the same thing. But if what you have doesn't quite match up with what the rule looks like, change what you have to make it match up with what the rule looks like. Now, look at one more rule for us. If you've got this scenario, say you wanted to do the integral of a multiplied by e to the bx. So you want to integrate that. Now here is an exponential. Now we know that exponentials, when you derive them, they give themselves. So when they integrate, they must also give themselves. So the rule here is going to be integral of a e to the bx will be a e to the bx all divided by b. Don't forget your plus c on the end. And that's another rule that you need to know for integration. So those 4 situations, the integrals of polynomials that I started with, this simple basic rule here, this here with its variation, and then this one here for exponentials. Put all that together in exercise 4.2 from the old textbook. You'll have everything you need to be able to get those out. We don't do any of the trigonometry ones, so anything that's got trig in it, leave them alone for the time being. We'll do that later in the year, but everything else is well within your grasp now doing. Good luck with that.